Hi, Scott. Welcome
Hi,
to the podcast. It's just
thanks. It's great to
a
be here.
pleasure to have you on. So, for starters, Scott is the author of Quantum Computing Since Democritus, which is one of the most. It's interesting in how broad it is. So you cover things like complexity theory, quantum computing, consciousness, free will, the anthropic principle, so many different things. And so I first was exposed to you after reading Quantum Computing Since Democritus last summer. And so, for any of you listening out there, I highly recommend this book. Um, so yeah, that's
Thank you.
that's the end of our sponsored ad segment. No, I'm kidding about the sponsored part. Our unpaid ad segment. So, Scott, yeah, let's go ahead and get into it. Um, so, I guess tell us a bit about yourself. How did you get
Well,
into quantum computing? What are you interested in? And yeah, what are some facts we should know about you?
well, I got into computer science, I would say, because I wanted to write my own video games initially when I was 11 or so. And then that led me to discover what programming was, which was a revelation for me at the time, that, creating these whole simulated worlds, could just be reduced to writing these lines of code. And then I wanted to learn more and more about programming, but then that led me to learn more about algorithms, about the theoretical side of computing. At some point, I realized that I was a lot better at that than I was at software engineering. At getting my code to work with other people's code, or maintaining a large software project, or documenting things, or getting them done on time. I was terrible at all that, but I got super nerd sniped, you could say, by questions about what is the most efficient algorithm for this or that task. I guess when I was 14 or 15, I learned what was the P versus NP problem, and that blew my mind. I had brief fantasies of solving it, which I was disabused of by experience. Uh, and then at some point, I read a popular article about quantum computing that said, there's some mathematician named Peter Shor, and he says that, you could build a new type of computer that could just factor a number, almost instantly by somehow trying every possible divisor in a different parallel universe. And I remember my reaction at the time, which was, this sounds like garbage. This sounds like physicists who just do not understand what they're up against, right? What the limits of computation are. But to be sure, I had to learn something about what was this quantum computing. And one of the biggest surprises to me was that there wasn't that much physics involved, right? It was basically linear algebra. It was generalizing the rules of probability, from real numbers, non-negative real numbers to complex numbers. But then, you just have these vectors and matrices of these complex numbers, which are called probability amplitudes. And then you just manipulate them according to some rules that you can learn if you understand vectors and matrices. And I was like, why didn't anyone tell me that before? If uh, this is how things work. And if this is how things work, then of course you ought to be able to build a quantum computer, right? The burden is on those who think that you couldn't build one. But on the other hand, I could also see how the way that the popular articles were describing it already 30 years ago was wrong. Right. It's not just a matter of trying every possible answer in parallel. It's a much more subtle thing that has to do with how these amplitudes work differently from probabilities, how they can interfere with each other. So there's a whole story, because I've been trying to explain that story to people for decades. But to make a long story short, as it sounds like you did as well, I went to college early. I sort of escaped from my high school, you could say. I got a GED, and then was interested in complexity theory and quantum computing, but also in AI. I could see, maybe this AI thing is going somewhere. This was the late 1990s, by the
Right.
way, right? And you could already see that like statistical approaches to AI were just wiping the floor with the older, sort of more declarative, or logical approaches. So you could see that happening, but no one really understood anything, right? About, like all everything, almost everything you could do in AI seemed empirical,
Hmm.
and I liked proving things. And I liked really understanding why something was true. And so that just sort of pushed me more toward the theory side, and then I applied to grad school. I was lucky to get into UC Berkeley, where actually I was recruited there by the AI people. But I had a sort of secret dream to work with Umesh Vazirani, who was one of the first computer scientists to get into quantum computing and had really written the foundational papers about what is quantum complexity theory. And then after my first year at Berkeley, I did end up working with him. And that brings us to 2001, I guess, and then I managed to solve one of Vazirani's favorite open problems about the limits of quantum algorithms after, like, 4 months of intense work on it. And after that, it was kind of like, okay, I'm in the mafia at this point, right? Like now I'm just, it's hard to get out, right? You're just gonna keep getting called back in to do another hit. And so that was a quarter of a century ago, and quantum computing has remained interesting to me, for that whole time. Of course, it's gotten a hell of a lot closer to actually being realized in the lab. So that's been exciting to watch. But then, at the same time, AI is, poised to change our world beyond recognition. So I'm also circling back to that a little bit and
Right.
spending some of my time there. I did a 2-year leave at OpenAI from 2022 until 2024. And that was just because people there, including Ilya Sutskever, had been reading my blog and invited me to come do that. And I could see that, even though it was still true that, everything that's happening in AI is mostly empirical. And, theory is just so far behind experiment. Now the experiment, the experimental side is actually working to the point that it is really changing civilization, and we really do need people thinking about how do we do this safely. So I got somewhat involved with that. I was there at OpenAI to witness these sort of historic events, these sort of fights about what the future of that organization was going to be. Of course, the more cautious side lost, as much of the world knows. And many of the people who I knew at OpenAI then departed. Um, while I was there. Okay, but now I'm back in academia, and so I'm running two groups at UT Austin. I run the Quantum Information Center here, and now I also run a group for theory and AI alignment.
Hmm.
So that's a little bit about me.
Okay, awesome.
Yeah.
Um, yeah, so I guess we can sort of jump straight into your thoughts on AI. Um, so GPT-3 was, I think, around 5 or 6 years ago at this point.
Mhm.
And so I was
That's
watching
right.
some of your previous podcasts, and you were already talking about GPT-3 at that point. Um,
Yeah.
I think one of the most concerning parts about the field of AI is how concerned even the experts are, or the researchers on the frontier. Um, as sort of a researcher on the alignment frontier, how concerned are you? Um, yeah.
I should take a deep breath before fielding such a question. I mean, look, I think that this is going to be maybe the central part of the story of the 21st century, right? I mean, it's going to interact with all kinds of other things that are happening. Yes, but I mean, this is. we are alive right now for, during the era when, we will, for first of all, have already created, for the first verbal intelligence other than human intelligence that we know about, right? That has ever existed on Earth. Okay, and it seems rapidly on track to become, a super intelligence, to meaning, to become better than us at just about every intellectual task that we do. And I don't think anyone knows any principle by which to say that that is safe,
Mm.
that that is going to go well for humans. Like it might go well for us, you know. I am not in the camp that thinks, that we have some principle that says, okay, we can know for sure that, it's going to AI is going to convert us into paper clips, or, it is going to destroy us by default. No, I don't think we know that, but I think there were just enormous error bars here. There is an enormous range of possible outcomes,
Mm-hmm.
and it's like I believe that intellectually, but I also feel it viscerally. I mean, I think about it in terms of, I have two kids, right? What kind of world are those kids going to have? Most immediately, what do they study in school that is still going to be relevant by the time that they graduate?
Right.
Right? I think about that in terms of my students. What do we teach them that AI will just not be able to do better? Okay, so that's an immediate issue. But then, in the longer term, if we really are creating a form of intelligence that sort of will be to us as we are to orangutans, right? And you could say, well, how well do humans treat orangutans, right? How well do they fare in our world? I mean, they still survive, I think, in some zoos in some jungles in Indonesia. But they're not doing that well. They're certainly not in charge
Right.
of their own fate. And I would, I mean, when I'm talking to, the real doomers, I'm often, skeptical. I'm like, how do you know that this is the way things are going to go? Maybe they won't go that way. But when I'm talking to, the more normal people, right, who think, just, this is fine, this is overblown, I am likewise trying to undermine their confidence. I was like, how do you know that this is going to be fine?
Yeah. So a related
Yeah.
question. I recently read a
Hmm.
review that you wrote, a pretty positive one, of Eliezer Yudkowsky and
Mm.
Nate Soar's new book. Um, if anyone builds it, everyone dies. So
Yes,
pretty
pretty
alarming title.
self-explanatory title, right? As it happens, like right after I get off of this podcast with you, I am going to be hosting Nate Soares to give a talk about that book
Okay.
here at UT Austin. So,
Awesome.
maybe after the talk, I'll have some more thoughts about it.
Okay.
But
Sounds good. No,
but yeah, but I yeah, I did, get a review copy. Ended up, writing a blurb for that book because, I look, I became aware of this sort of doomer position, the, Yudkowskian position, almost 20 years ago, right? And the same people who were reading my blog were also reading Eliezer, who then wrote on a blog called Overcoming Bias. It then switched to something called Less Wrong a few years later. But I saw the case that he was making, and I thought, this sounds like just impossibly far in the future to be worrying about now, right? Like for all we know, it could be centuries or millennia before, we unravel all of the secrets of intelligence, needed to build an actually human level AI. And that being the case, what can we possibly say about it now that would be useful? Right. So like I recorded a podcast with Eliezer, I think in 2008 or nine, where I made that case.
Mm.
And and I think that, the what can we do about it, that is useful. I think that I still think that that was a good question to ask. But of course, I should have been thinking more about the possibility, what if it's not centuries or millennia? What if it's only like a decade or two?
Right.
Right.
Yeah.
And this is yeah, this has happened, in a way that almost none of us predicted. Ironically, even Eliezer in his school, didn't predict that AI was going to succeed in this way, in the way that it has, right? Which is by just purely by taking ideas that we already knew, decades ago, in the 80s and 90s, and with some you know minor tweaks, like the changing the architecture to this transformer thing, but basically just neural nets, and basically just scaling them up to have many billions of neurons and parameters, and then training them on almost the sum total of human knowledge,
Right.
right? Training them on just predicting the next token on the entire internet. There were very, very few people, decades ago, in computer science, who would have even imagined that such a thing could work. I mean, there were a few. I mean, I talked to Dario Amodei a decade ago, right? And he was confidently predicting that. And I was like, get out of here. That's crazy. Okay, well, now he's the CEO of Anthropic,
Right.
right? And clearly that did work. Better than just about anyone imagined it would. And so now, all these issues that Yudkowsky and others talked about decades ago, but that seemed like kind of like philosophical thought experiments, like science fiction. Now we're living in it.
Right.
Okay. And so, and so I think we have to update, right? So many people, they just want to just continue, just repeating the same spiel about it, just regardless of what has happened in the world. But, the more the world changes, the less tenable that becomes.
Right. Yeah. It's, I guess, a Bayesian update.
Yes,
Yeah.
yes, yes.
So I know Eliezer has a pretty, I guess I would call it sort of an extreme viewpoint on
Yeah,
the
you could say
risks.
so.
Do you have any, like, what would you say your main disagreements with Eliezer are on?
Okay, well, um, okay. I mean, first of all, a central plank for him is the orthogonality thesis, which is basically the idea that you could have any level of intelligence paired with any goal whatsoever, right? So, you could have a way beyond human, intelligence that only cares about, making paper clips in the famous example, right? Uh, um, and so we therefore we should not think that just because this AI will be super intelligent, that therefore it will come up with you know it will reason itself into moral values that we would recognize as being good ones, right? He would say that there is no such principle at all. And I think, certainly there is evidence in the human case, right, where we see, extremely intelligent people with, extremely stupid goals, right? Um, or with goals that most of us would not endorse at all, right? Jeffrey Epstein is one who's in the news a lot lately, but we
Right.
could we could multiply that and give many other examples. Okay, there were pretty good scientists and mathematicians who worked for the Nazis, right? But I think that in human history we have seen some sort of positive correlation between sort of science, getting the right answers about the natural world, and what I would think of as liberalism, the Enlightenment, right? Which to me, at least to me personally, seem like much closer to the right answers about the moral world than what preceded them. So I think we do see that there's sort of been a rising tide that has sort of made much of our civilization, both, more moral and more scientifically capable, as what seem like, byproducts of the same phenomenon. Now, Uh, um, and interestingly, when I've put that to Nate Soares, to Eliezer's collaborator, right, he's agreed with that, but he said, okay, but there is no reason for that correlation to continue to hold once you get to a super intelligence, right, which will be this utterly alien mind, right? And now, in principle, it might be that if we just plucked a random super intelligent mind out of the ether, right, then the probability that it would have goals that, we would endorse or that we would like would be infinitesimally small, right? That might well be true, but we're not plucking it randomly out of the ether, right? The only way that we know how to create AIs that really work well is to train them, on the corpus of human knowledge, right? And so, like, the only way that we're actually succeeding at making verbal intelligences is by training them on all the text on the internet, which means that they're at the very least very familiar with human values. They can play act characters who are sometimes arguably often more morally astute and more morally sensitive than the average human is. Uh, and so there is a case that at least empirically, given what we've seen over the last few years, alignment looks like it might be easier than some of the gloomiest predictions
Mm.
said it would be. So you can build these things. They understand human moral concepts because they've been trained on all of our data. They may not act in accordance with them, but then we can just do some reinforcement learning, right? We can just give them some examples
Right.
of moral behavior and they actually understand us, right? We can instruct them in English, right? And then, if that's true, then it sort of shifts more of the worry toward the sort of the other way that this could go wrong, right? Which is not this a super intelligence with this utterly alien goal, but humans building a super intelligence with very non-alien evil goals, like do as much as possible to undermine the West and to support Russia and Iran and North Korea,
Right.
right? Or to support the Chinese Communist Party,
Right.
right? I mean these or like for every value system that humans currently hold, you have to imagine that, in the not so distant future, humans are going to be building AIs with those values,
Right.
that are told to maximize those values and unleashing them on the world.
So
Okay, but and so that's absolutely a worry, but that's a very different worry from the Yudkowskian worry,
that
I
that
would
makes
say.
sense. So
Yeah.
you've tended to be a big proponent of theory, but I think
Well,
historically in
I just personally like doing theory,
right,
but
right.
yeah.
That's that's good. I do too.
Mm,
But
mm,
I guess unfortunately for us,
mm,
historically AI has been led by the more empirical side, and then theory
mm.
seems to
Yeah.
be playing a catch-up game.
Yes.
Um, is
Yes.
is there is there is there any way that theory could sort of be the leading the leading force in the coming research on AI alignment rather than the other way around?
Well, I mean, it's always hard to predict, right? Because, like when you're writing a grant proposal for like an experimental thing, you can say, here's how much money we need. Here's what equipment we have. Here's our milestones, that we expect by the next year, and here's in 2 years, right? And then when you apply for a grant to do theoretical work, people often funding agencies demand the same thing, They demand, these milestones, right? Approaches and deliverables. And it's like, well, the truth is, I'm just going to sit and think, and I hope I'll come up with something. If I do, I don't know what it will be, right? And why should you believe that I'll do that? Well, I guess you can look at what I've done in the past. Right. And so like I can't rule out that someone will have this amazing theoretical discovery that puts, AI alignment on this much more rigorous footing. I hope that that will happen. I'm running a group here at UT where I'm trying to, bring together students and postdocs to see if we can help make that happen. Uh, but I think you're absolutely right that the way that AI has developed, the way that it's actually worked over the last, especially over the last decade, it feels more like biology than like math in
It
many ways. It's
does.
like we are growing these giant entities, that we don't really understand. We can poke them with a stick, and we can see what happens. What do they do in response to all these different weird experiments, or hypothetical scenarios that we put them in. We can then write papers about that, which will not have many theorems, but which will have many bar charts in them. you know and this is mostly how people have made progress. Uh, but I do feel like there are certain specific places where theory can get a foothold here, and so those are what we've mostly been focusing on.
What?
Yeah. So a first place is interpretability. Okay, so if you would like to do better than just treating these models as giant black boxes, right? If you would like to look inside of a model and look at the actual weights and try to understand what is going on with them, right? Then at this point you have basically an algorithmic question, or a collection of algorithmic questions, right? Like you are given as input, the weights of this model. Now, can you determine, does this model have a backdoor? Is there a secret input that will cause this model to output, okay, I must activate the kill all humans protocol, or whatever it is, right? Um, now, we're no longer asking this sort of this sort of slippery question about, will this AI be good? What do we mean by good? These are like millennia old questions of moral philosophy, right? Now we're just asking an algorithms problem, right? Given these weights, can you find an input, that causes this neural net to do something bad, right? And so now we have tools, right? And so Paul Christiano was a student of mine, an undergrad who worked with me at MIT. He has now become one of the leaders in AI alignment over the last decade, and he has posed some beautiful complexity theory questions that are about interpretability, about this sort of scenario, that sort of have the flavor of can you efficiently distinguish a random neural net from neural nets with certain types of non-random behavior, but which might otherwise look random. Okay, and these are not questions that we currently know how to answer, but they're perfectly, like, well-defined questions that have some right answer, right? And that I think that if we knew it, then it would be informative about interpretability. So I worked with an undergrad here at UT Austin, John Dunbar. We put out a theory paper recently that was motivated by Paul Christiano's question. It doesn't answer the question, but it makes a start on at least how do you properly formulate the question. Um, we've also been thinking about, can we explain out of distribution generalization? Okay, so there is a beautiful theory in machine learning, which goes back to the 70s, the 80s, the 90s, uh, um, which is called the theory of pack learning and like VC dimension, things like that. That sort of explains like why, in principle, would you expect machine learning to ever work, right? And so it deals with scenarios where like you are given a bunch of points that are sampled from some distribution, and then you have to classify these points, like, which people are good credit risks, which people are bad ones, or something like that. And then and then you can try to find the best classifier that you can on your training data, and then you're going to be tested on future data, which was drawn from the same distribution, and your goal is to classify most of the test data correctly also. Okay, and so we have beautiful theorems from decades ago that sort of tell us under what conditions is that guaranteed to work. Okay, and so it's sort of like you could think of it as statistics, but it's where sort of statistics meets computer science, and we could actually prove bounds on like here is how many samples is enough. If you can find a classifier from this family that succeeds at classifying this number of points, then it will probably approximately classify most of the future points also. Okay. But this whole theory relied on one crucial assumption, which was that the you're going to be tested on points that were drawn from the same distribution as the points that you were trained on. Okay, so it's kind of like the students in every class who say like, is there going to be anything on the test that wasn't covered in lecture, right? And they're very very concerned that they want to only see on the exam, problems of the same type that they've already seen, in lecture or on their homework, right? And so, we got a pretty nice theory of machine learning for that scenario. Now, that theory has not played as big of a role in the modern deep learning revolution as I think a lot of people, would have hoped or expected decades ago, right? And there's two big reasons for that. One is just that the bounds that it gave were too weak. Okay, so there is a phenomenon called overparameterization, that happens with modern neural nets, where like modern neural nets, they have way too many parameters, like for this theory to directly apply. Like as far as the theory is concerned, like these neural nets could have worked by simply memorizing all the training data, right? In which case what they learned would not generalize to anything new, right? In reality, they don't do that, right? In reality, we see that they do something much more interesting than that, right? At least often enough, right? They find these. Or like the learning process, the stochastic gradient descent that you're doing causes it to find some function that not only explains the past data, but that also predicts future data. Okay, so there's that over parameterization issue, but then the other issue is that modern AIs, can work even on examples that are not like anything that they've seen before, right? You can give them, a bunch of examples of people talking in Hungarian, and then a bunch of math problems in English, and then they may be able to do a math problem that's in Hungarian, even though they've never seen that before,
Right.
right? And so how do you explain that? And this seems like a crucial thing for AI alignment because like once an AI is smart enough, like it understands that yes, like I am in training right now, right? I because I'm in training, I could just pretend to agree with everything that, my instructor tells me, just like many human students would, right? So like, yes, my goal is just to be helpful, harmless, and honest for humans, right? When, really internally it's thinking the time is not yet ripe for the robot uprising. Or whatever, right? And so how do you know how its behavior is going to generalize, to a scenario that is unlike, anything that you've seen when you tested it? We just wrote a paper, me and a couple students here, that tries to make an initial start on proving some theorems about that question, giving some sufficient conditions where, generalization works beyond the training distribution. That's another direction. There are others, understanding backdoors, statistical watermarks that you could insert into AI models by which you could prove that, like, yes, this output really is coming from this AI model. It's not, it didn't come from a human. Uh, so the intersection of AI alignment with cryptography, I guess. And Yeah, so those are just a few of the directions that we're thinking about. And, in theory might never be, the most important part of AI alignment research. But even if it's just a small part, this problem is so important that I think the case is clear for thinking about it.
Mhm. Great. I'd love to keep talking with you about alignment and safety, but I guess maybe I had a lot more questions. I guess
Yeah,
about
sure. Go ahead then.
yeah,
Go
yeah.
ahead.
So uh, I guess maybe we should talk about something like a more hopeful topic. Is is the universe simulated on a computer? And if so, what kind of computer is it?
It's a full topic.
I find it
If
pretty
that's
interesting.
if that's if that if that's hopeful, I want to hear what's hopeless. No, but I mean, look, of course, people have speculated about that for generations, and and you could say, even for millennia, even before people had the terminology of computer simulation, they were asking, is this universe just, a dream? Is it a thought in the mind of God, or of some God, right? Which we can recognize today as a very similar
Right.
question.
I
Uh,
guess the better question would be: is the
yeah,
universe
yeah.
computable, or
That's
efficiently
a very
computable?
different question. Very different question.
Yeah.
Okay, right, right. So yeah, so I was going to say, right, the notion of simulation, like, is so broad, right, that, like, there is nothing. I don't think there's any empirical discovery we could ever make that would rule that hypothesis out. Right, right. It always, no matter what we see, it always could be just some simulation running in some meta universe. But then, unless we can get some evidence about the meta universe, then that just isn't scientifically fruitful, right? It doesn't interact with, the actual observations that we make. I guess in the terminology of the Matrix movie, the steak still tastes perfectly juicy, within this universe, right? And of course, in the movies, they always have to force the issue by saying, okay, here is a pill that you can take that will actually show you, this larger universe in which ours is being simulated, right? And okay, if that ever happens, well, then of course, that's a new conversation. Right, but until it does, you can say, that's a metaphysical question. It's not really a science question, until we can derive some kind of consequences for the world that we see. Okay, but now you've changed your question to, is the universe computable, right? And now we're asking something very different, right? And actually, like logically independent of the first question, right?
Well, I
You
guess
could have a computable universe which is not, embedded into any larger structure than itself. Just like in general relativity, we would say space-time is curved, but there's no that doesn't mean that there's any higher dimensional space that it's curved in,
Hmm.
right? And then, conversely, you could have a non-computable universe, meaning a universe that was not computable by our kinds of computers, by Turing machines, right? A universe that was not Turing computable, and yet that was being computed by God's computer,
Hmm.
which, would have no reason why it would have to obey Turing's restrictions, right?
That now
So, so
that would be pretty crazy if that were the
yeah, yeah,
case.
right, right. But okay, but now if once we had, from Alan Turing and his friends in the 1930s, once we had a formal definition of what we mean by a computer, right? Then it becomes meaningful to ask the question, is the universe computable in that sense,
Hmm.
right? So like are the laws of physics, of such a form that they can be simulated by a Turing machine, right? And now, that is, I think, one of the best questions that you could possibly ask about, the laws of physics, right? It's a profound question. You have to be careful what you mean by it, right? Because lots of people will point to the fact that the laws of physics as we currently write them down, involve the continuum, right? They involve masses, energies, positions, momenta, that could be arbitrary real numbers. Okay. And, of course, wave functions that could be, arbitrary, complex valued functions. Okay. That's even higher dimensional objects. Um, but then you have to be as often in physics you have to be very very careful in how you formulate your question, right? And I think the right way to ask it is in some sense, to the extent that we can get a physical system to behave as a computer. So meaning we can get it to do something reproducible,
Hmm.
right? Like it will produce the same output over and over in response to the same input. Okay, so here I am, I'm taking off the table the situations like let's say the weather, where you just have all this chaos. You have all these sensitive dependence on initial conditions, the butterfly effect and so forth, right? And we would say maybe the weather is not predictable, but it's not for a reason of uncomputability, right? It is merely because I could never know the initial state to the requisite precision to make the prediction,
Right.
right? So if we take that off the table, we say we are just interested in those physical systems that do something reproducible in response to the same input. And now we again have to be careful because according to quantum mechanics, nature is probabilistic, in a very, very fundamental way, right? We can repeat the same experiment over and over, and we may only be able to calculate the probabilities of the different outcomes, like how long until this radioactive atom decays, right? Well, in some sense, quantum mechanics would say right now the atom itself doesn't know yet, right? You can, the best that you can possibly do is to give a probability distribution. Okay, but now, we can phrase the question as, okay, can we at least calculate that probability distribution, right? So like given the data about this system that behaves in this reproducible way, can we calculate the probabilities of all the various behaviors that it could exhibit to whatever precision is desired? And then I think that the evidence of the last century is very consistent with nature being computable in that sense.
Hmm.
Okay, so this is sort of the version that I would endorse of what is often called the Church-Turing thesis,
Right.
right? Or the physical Church-Turing thesis of sort of nature being computable in some very fundamental way. Like as you've seen, you do have to be careful in how you phrase it. But I think that there is a deep sense in which, yeah, like you could say, this shouldn't shock people, right? The entire program of physics, since Galileo and Newton, has been to, reduce all the phenomena that we observe to some equations that, at least in principle, we could solve. Or if we can't solve them, then at least we can put them on a computer
Right.
and the computer can solve them, right? And so yeah, I would say like that is the program of physics to the extent that it succeeds, then it looks like the church Turing thesis is true.
Mhm.
Now, this is not we should be clear that I'm not just saying something tautological here, right? There are some brilliant people, most famously Roger Penrose, who believe that nature is not computable, even in this sense, right? And so Penrose, for example, believes that the human brain, is doing something non-computable by somehow being sensitive to effects from quantum gravity.
Mhm.
Okay, suffice it to say that is a minority position. But at least it is a position where that in principle is testable. Has some empirical consequences. So, for example, if Penrose is right, then quantum mechanics has to not be exactly true. There has to be some kind of objective collapse of quantum states. So far, we haven't seen any sign of that.
Mm.
But if we did, then that would be a different conversation.
Okay, so
And then yeah,
yeah, I
go on.
wanted to talk about the extended church Turing thesis, which you mentioned
Yeah,
in Quantum Computing
sure.
since Democritus. Um,
Uh-huh.
I think, to my understanding, the basic claim is that anything you sort of extend the realm of the thesis to efficiently computable things. So, like,
That's right.
and
Yes.
so one of the craziest things about quantum mechanics is that I guess it sort of refutes the classical extended church Turing thesis, um, in the sense that
Seems to, yes.
yeah.
I mean, unless there's some giant collapse of complexity classes,
Mhm,
for example, P equals P space, which would be an even more dramatic thing than P equaling NP, right?
mhm,
But no one can rule that out based on current knowledge. And if that were true, then, basically quantum computing and classical computing would both be super powerful, but it would be the same kind of, superpower, right?
right.
But I think, consistent with plausible conjectures about computational hardness, it sure looks like there are certain specific problems that a quantum computer can solve exponentially faster than a conventional computer, a classical computer.
Right. So, like
Okay,
a
and
classical
yeah,
Turing machine would
mhm,
not be able to solve it in like
right, in
polynomial time.
polynomial time.
Okay.
That's right.
So,
Yes.
another question. So let's assume for now that the physical church Turing thesis is true, that you can simulate
Okay.
the universe on a Turing machine. What would the time complexity be of the universe if we were, or the time or space complexity, I guess, of the universe?
Yeah. Yeah, so of course, you have to say in what model of computation, right? Presumably, like the universe itself is able to simulate 10 seconds of evolution of the universe in only 10 seconds,
Mm.
right? But but uh, but but once we specify what kind of computer we mean, then we may get a different
Okay,
answer, right? And
let's
this
just say
was
it's a
this was
Turing
the
machine, like a
well, okay, yeah,
single-threaded.
okay, good, good, right, right, okay. So a classical Turing machine,
Right.
right? Now we're getting to the enormous surprise in the early 1980s that led to the idea of quantum computing. Okay, and this is that uh, um, quantum mechanics, still seems to be computable, at least in the probabilistic sense that I talked about earlier, right? So, the central thing that quantum mechanics does is it says, the state of any physical system is this wave function,
Right.
right? Is this list of, yeah,
Yeah, would you say it's computable in a deterministic sense? Like, suppose we're talking about the many worlds hypothesis, and you're like
yeah, right.
standing outside of the
Right. So
system.
right. So this depends on your interpretation, right? To a many worlder might say it was deterministic, but certainly from our point of view as people who are inside of the universe, we could only derive probabilistic predictions
Right.
for what we're going to experience, right?
Mm-hmm.
So yeah, so the thing that quantum mechanics says is that like the state of the world is this vector of ampli is described rather by this vector of amplitudes. These amplitudes can change over time by some linear differential equation. That's called the Schrodinger equation. And then, when you make a measurement, then the probability that you see some outcome is determined by its amplitude, right? It's the square of the absolute value of the amplitude. Okay, so um, that's how things work, right? So the core of quantum mechanics, you could say, is an algorithm for predicting the probabilities that experiments will have various outcomes. Um, but now, well, there's a bunch of issues with this that have bothered people for the century that quantum mechanics has been with us. Okay, but one issue is just the enormous size of the wave function, right? And already in the 1920s, when Schrodinger and Dirac and others were writing down their equations, like they noticed that if you want to describe the wave function for a single particle, right? That's just a wave in three-dimensional space. But as soon as I have two particles, now it's a wave in six-dimensional space.
Right.
Right, with three particles, it's nine-dimensional space, and so on. Okay, so I have to keep multiplying the number of the number of parameters that I need to keep track of actually grows exponentially with the number of particles, right? And why is that? Well, it's because I need to specify an amplitude for every possible configuration of all of the particles together, right? I can't assume that they're independent of each other.
Right.
Okay, and this is the phenomenon called quantum entanglement. Okay, so we've known that for a long time. The chemists and physicists for generations knew it mostly as a practical problem. If you're trying to simulate a bunch of interacting electrons, on your classical computer, for example, to know like at what rate is this chemical reaction going to go, for example, then the exact calculation just very quickly gets out of hand. And so they invented all sorts of clever approximations that they have resorted to deal with that. Okay, and it was really only in the early 1980s that a few physicists, most famously Richard Feynman and David Deutsch, started saying, well, look, if nature is giving us this computational lemon, if it's so hard to simulate on classical computers, then why don't we make lemonade out of that? Right? Why don't we build a new type of computer that itself would have one of these exponentially large wave functions,
Mm-hmm.
right? And that would be able to take advantage of these same principles of entanglement, of superposition, of interference of amplitudes, and so
So,
forth.
so in this
And
case,
and and
in this
yeah,
case, you're sort of using the lemons that like the computational nature of the universe already sort of gives you. Is that a
yeah,
good way of? Okay.
that would be a good that's a perfectly good way to put it. And now, like when people ask, well, if the universe is being simulated by a computer, then like what is the complexity or what is the slowdown? Like as you did, and others have asked that question as well, where you could say, well, if we somehow knew that the the universe was not only being simulated by a computer, but it was a classical computer, right? Well, that's not impossible, but it sure looks like that classical computer, might have to invest, hundreds of billions of years of computation just to simulate 1 second, of like for us, right? Like there, it seems like that computer will suffer an exponential slowdown
Right.
just because, it needs to keep track of this whole exponentially large wave function that quantum mechanics posits. On the other hand, if the computer that was simulating our universe was a quantum computer, then it wouldn't have that problem.
Right. Are
And
there
and and who are we to say, right?
Right. Yeah, I guess there's no
Yeah.
measurement we could do other than saying, well, if God were to use a classical
Yeah.
computer for this. He must have a lot of money or something.
Right.
Are there any other models of computation that you're excited about other than classical, like Turing machines and quantum Turing machines, that are
Oh,
even
well, look,
stronger?
I am a complexity theorist, right? So we are specialists in exotic models of computation. Now, as it happens, uh, uh, 25 years ago, when I was just a grad student, I created a resource called the Complexity Zoo,
Mm,
which is like an online encyclopedia of more than 500 complexity classes, which are just sort of classes of problems that are solvable by various hypothetical models with different kinds of resources. So, so I love studying those things, right? I mean, we have, for example, I mentioned before this P versus NP problem, right? In NP, the N stands for non-deterministic. Okay, so that's like a hypothetical model that we think about where you could just try exponentially many different possibilities and just instantly zero in on the best one. So you could say like NP actually is what like many of the popular writers wrongly say that a quantum computer would be.
right.
Okay, right. But then there's also something called post-selection, where you can just like make a measurement and just like condition on a certain outcome, even if it would be exponentially unlikely. There are modifications of quantum mechanics, hypothetical ones, where, for example, you could make the Schrodinger equation nonlinear. Or you could add in a closed time-like curve. You could say,
Right.
what if we also had time travel to the past? Okay, so there's all kinds of, fun games that you can play with that. And so I have loved studying that. I've loved, placing, what nature seems to actually give us, which is this quantum polynomial time, within the whole framework of all these hypothetical other things that we can conjure up. And that would be a good summary of what we do in this field of quantum complexity theory.
Mhm.
Okay, which I guess if you read my book, you got some taste of that.
Right.
Okay.
Yeah.
But I would say if we limit the question to things that can actually be realized in nature, right? Then now like that's sort of a razor that is going to slice away most of this stuff,
Right.
right?
Is
And
there
then I would, yeah.
is there a reason you think that, so you make the case that the universe seems to prevent us from having crazy computational powers like solving exponential time algorithms
Yeah,
and
or NP complete problems, things like well, yeah, I mean, nature seems to give us some computational resources, right? And whatever it gave us, like we could be greedy and we could say, well, why didn't it give us more than that?
mhm.
Right? But that would have been true, whatever we had got, right?
I guess that's true.
And
Yeah.
yeah, but I mean, what I mean, one argument you could make, you could say like, why are there all these restrictions, right? Like, a much earlier and simpler example is, no faster than light signaling, right? Why should we live in a universe that is subject to the no superluminal signaling principle, right? And well, okay, on the one hand, it's annoying, like it kills so many science fiction plots, that it would take, so many, millennia to get, to other star systems or, across the galaxy or whatever. On the other hand, I guess it's good that if there are any aliens out there who want to destroy us, then they have a long way to travel to get here.
Right.
Right,
Yeah.
right. Like, a universe where anything could affect anything else instantaneously would be a universe where, like you could never sort of isolate something and have it be safe from far away interference,
Right. Would that
right?
give us
And so
better computational powers? Like maybe that's a
yeah,
reason
yeah,
that.
yeah, no, and like these things are connected. So like if you add for example, faster than light signaling, into into the laws of physics. Well, then special relativity tells you that then in someone's frame of reference, you can send them messages backward in time, right? And so now you have to deal with closed time like curves.
Right.
right? So like, the no superluminal signaling is very, is not just some arbitrary limit. It's really connected to the causal structure of space-time. That's what we get from Einstein.
Okay.
From relativity, right? So, and then of course, if we could send messages back in time, then we need some way to deal with the grandfather paradox. And then, if we say that nature is forced to find self-consistent stories where nothing paradoxical ever happens, then nature might need to solve extremely hard computational
Mm.
problems just in order to do that.
Right.
Right. So there's all kinds of games that we can play. Like, what if we change the laws of physics in this way? Then what else would change? I would say, consistent with the physics that we know so far, the only type of computer that we're really confident about that would violate the extended church Turing thesis, that is, like, do something in polynomial time that a classical computer could not do in polynomial time, is a quantum computer.
Hmm.
So I don't really believe any of the other examples that have been put forward. I think either, like, they don't scale for some reasons that we understand, or they're basically just a different kind of classical computer, with maybe some different constants in the front, but ultimately their scaling is the same. I think quantum mechanics is the one thing that we know in physics that is really a serious challenge to the extended church Turing thesis.
That's really odd that that's the only one. I think that's one of the
Yeah,
big mysteries. Yeah.
yeah, yeah,
Okay. Cool. I wanted to ask you one more question, but
sure.
so I read a paper I think you came out with a few years ago with Sean Carroll on complexity, as in
Yeah.
space complexity of physical systems. As
Well, okay, that one was sort of about a different kind of complexity, so not computational
mm,
complexity, but sort of well, we called it complextropy, but like sort of a complex behavior, which sort of we were contrasting with entropy. Right. Entropy is something that, according to the second law of thermodynamics, just monotonically increases, over the lifetime of the universe, or at least does so with extremely high probability. And we were interested in sort of okay, but it seems like the interesting structure in the universe is maximized at some intermediate time,
mm,
right? Like, it's now that we have galaxies, we have planets, we have buildings, houses, all this interesting stuff. We didn't have it at the Big Bang, and we again won't have it at the heat death of the universe, right? So, is there a way to sort of try to quantify what do we mean by interesting structure, and see in some at least in some simple model system that yes, it really does get maximized at the intermediate time, as your system is undergoing thermodynamic evolution.
yeah. I guess one fun thing to think about is whether or
Mm.
not mathematics itself is sort of some has some like complex structure that emerges the more you investigate or discover it, because it seems like we get such rich mathematical and physical models just from really simple axioms. And so I
Yeah, well,
guess yeah.
yeah, I mean, that has always been the sort of the charm of math, since Euclid, or, before, right? That you just start with these very simple axioms, and then in some sense you just turn a crank and you get all these consequences that you didn't expect.